Alright, so we'll just get started here, I'm sure. Oh, sorry. Crystal will be here shortly. So yesterday you had this introduction, or no, this is today. Yesterday you had the KSP quiz, so please do try and take that as soon as you can if you haven't taken it already. I'll be grading that shortly, as well as the other KEQ test. Okay, the one that was with this one. Yeah. Today, though, we're starting a new unit on acids and bases. So there's a couple things that you guys can look at here. The first thing is the success criteria here. You don't need to do a SQ3R for this one. Okay. So don't worry about the SQ3R. This unit is, we've talked about acids and bases in the past. We're going to go a little bit more in depth with them in this unit. And then we're going to talk about Ka and Kb, as well as what Kw is. And that is very much in line with like KEQ stuff. So equilibrium type stuff. So very similar, but we're going to be it's with acids and bases now. And we'll talk, we really won't kind of get to that too much today. We'll talk very, very little about that today. All right. But we've done stuff where we've calculated like pH, POH, OH minus concentration, H plus concentration. You are going to practice a little bit of that today. Okay. But this unit is a little bit of a review, and then we're taking and extending it a little bit further, and now bringing equilibrium into this idea here with weak acids and weak bases. All right. I do have this is some notes that on the whole the whole unit here, or the whole chapter 14 that I've included. So if you want to ever check that out, you can. If you want to take your own notes, you can. I believe we've done a little bit of stuff on conjugate base, conjugate acid, but we'll talk a little bit about that today, and we'll practice. We're not going to practice it today, but or there's a little bit of practice today, but not a lot. Okay. Yeah. So, and then when we're done today, you have two things to work on: this acid-base properties of acids and bases. Again, something that we kind of covered in the past in like the first unit. And then also this pH, POH calculation stuff. Again, something that you've done before in the past. If you've had me for chemistry, we've done that. We've probably done both of these things a little bit. So you have some practice with those. So today's a little bit of review and a little bit of a new introduction here. So let's get started with that. As soon as it loads. Sometime today it will load. Yeah, so these are loading. So this one's pretty simple. It's just good practice to kind of write these things out, right? So taste, pH, all this. We're going to go over this today. Yeah, pretty much all this we're going to talk about today. So, and this is calculating pH, POH, H plus, H minus, so OH minus concentrations. Again, stuff that you've done, but there's some direction there too. So the answers are given to you on the side. All right. I just suggest that you practice doing it. I don't necessarily need you to show your work for this. I want you to just kind of check your own understanding and make sure you're able to do these things. Okay, I don't need to see the work. Typically, like with my chemistry class, I ask to see the work, but just make sure you practice it. Make sure you're getting these answers. Make sure you understand. And then if you have any questions, let me know. But it's really just practice. Okay? There we go, finally. Oh, it was running so fast before, now it's so slow. Even when I recorded my first period and it was going very quickly. Okay, so acid and bases definition. Acid, the actual word for acid means sour. There's also very much related to the word for vinegar, the Latin word for vinegar. Basically because before scientists got smart, they used to taste everything, right? They used to taste everything. We don't do that nowadays. You definitely do not just taste random chemicals, right? But most acidic things have a sour or tart taste to them. So things like yogurt, vinegar, lemon juice, citric acid, apples, jelly, pineapples. Milk is actually acidic, and batteries. Then the other one is bases. Now, bases, if you ever hear alkali, alkali refers to bases. Okay, so you'll hear alkali. Okay, and when they actually discovered how they actually discovered these bases were that they found that if you took the ashes of plants or burned matter and then mixed it with water, you'd get this soapy feeling substance. Okay, so you take the ashes and then you put it with a fat or oil, actually, really a fat or oil, and you'd get soap. Okay, you get soap. So sometimes you hear the word instead of basic, you hear them say that it's alkali. Alkali. All right, things that are alkali are drain cleaner, ammonia, bleach, toothpaste, baking soda, shampoo, chalk. Okay. Actually, how soap was actually discovered, and this is, I don't know if it's true or not, but this is the story that I've been told and I've heard, is that people were washing their clothes in the river, and then they noticed that their clothes would, when they put the clothes in the river and they would, they would wring them out, they got like this foamy stuff coming out, and then the clothes would get cleaner. And then they realized what was happening was they were burning bodies further downstream, and as the ash got into the river, it would react with the oil and dirt in the clothes to produce soap. Because soap is basically just take lye or sodium hydroxide or a base, and then you react it with react it with an oil, with any kind of oil, really, like fat, any kind of oil or fat, and when they react, they form soap. If anyone's ever seen Fight Club, anyone seen Fight Club? No. They make soap out of human fat. They take human fat from a liposuction clinic, they react it with lye, and then they produce soap. And they actually skim off the top of it, and on the top is a layer of glycerin, and you can actually use the glycerin to make dynamite or nitroglycerin. So, yeah, all that good stuff. Anyway, yeah, so acid, base, or alkali, Okay. The properties of acids and bases, again, acids taste sour. pH is generally from 0 to 6.9. Technically, they can be negative pHs, though. There can be negative pHs. They turn litmus red. I always just think acid red. They react with bases to form salt and water. They neutralize bases. They produce H plus ions. They're clear in phenolphthalein indicator solution, and they react with metals to produce hydrogen gas. Now, there is another definition of acid that we don't need to know, the Lewis definition of acid. And that Lewis definition of acid includes things that don't always produce H plus ions. But we're not going to be concerning ourselves with that. AP Chemistry doesn't cover the Lewis definition of acids and bases anymore. Okay. But if you do see it somewhere, just realize we don't talk about it anymore. We don't cover it. It's not part of the AP exam. If you do look in the book, I believe, and those notes that I gave you, that definition is included, but it's not covered anymore. So you can ignore it. Bases taste bitter. They turn their pHs from 7.1 to 14, although it can be higher than 14 technically. They react with acids to form salt water, so they basically neutralize acids. They produce OH minus ions. They're red in phenolphthalein, so they turn phenolphthalein red, and they don't react with metal. I'm going to add one little thing here, is that they either produce OH minus ions or they accept H plus ions. Oops. I'm presenting, aren't I don't know why I didn't have that here. Or accept H plus. Okay, next. So some facts here. Reactions between acids and bases are called neutralization reactions because they neutralize one another. Okay, an acid plus a base gives us water and a salt. They neutralize one another. Indicators. You can have indicators that are solutions. You could have indicators that are paper. Indicators are substances that change color due to pH change. Acids and bases are always electrolytes. And electrolytes, if you recall, are salts that produce ions in solution and conduct electricity. So acidic and basic solutions will conduct electricity. Both acids and bases can technically be corrosive. All that means is that if a substance eats away or burns at something, it's called corrosive, meaning it like breaks it down into simpler parts. It reacts with it. There are really two types of acids and bases, either strong acids and bases. Strong acids and bases we consider to completely ionize in water. So they will completely ionize. It will not stay together. It will totally form the H plus and the cation and anion, basically. Weak acids, however, weak acids and bases only partially ionize. So some of it will stay together in solution, and then other of it will dissolve totally and turn to ions in solution. And this is where we get the Ka and Kb. Weak acids and bases have Kas and Kbs. Just like some salts have KEQs, right, and KSPs. Some reactions have KEQs because they don't go all the way to completion. Some weak acids or all weak acids and bases have Ka and Kb because they don't totally ionize. Water can act as either an acid or a base. Okay, we call this property amphoteric. When something can act as either an acid or a base, we call it amphoteric. Water is the most popular one, but there's other things that are amphoteric as well, like HSO4 minus 1 or H2PO4 minus 1 or HPO4 minus 2. Those can act as acids and bases, and a lot of amphoteric substances, we can form buffers, and that's the next unit, and buffers are very confusing. Buffers are tough. I try and make that as simple and as easy as possible, but it's a struggle. Buffers are a struggle. It's a tough one. Okay, there's two definitions of acids and bases that we need to know. The first one is the Arrhenius definition. It's the simplest definition. An acid is any substance that produces H plus ions in water, and a base is any substance that produces OH minus in water. Okay, really, really simple. If it makes H plus when it dissolves, it's an acid. If it makes OH minus when it dissolves, it's a base. Along with the Arrhenius definition, and really the Bronsted-Lowry definition, which is the next one we're going to talk about, we can have 1 acidic hydrogens, 2 acidic hydrogens, or 3 acidic hydrogens. Okay, that's the most we can have is 3. I've never seen 4. There can't be 4. Okay, if it's 1 acidic hydrogen, we call it monoprotic. If it's 2 diprotic and 3 acidic, we call it triprotic. Mono, di, tri. Okay. The Bronsted-Lowry definition. The Bronsted-Lowry is the acid the same. However, the base, it is anything that accepts OH minus, including OH minus. So if it produces OH minus, then it's a base, and it's still the Bronsted-Lowry is fine, the definition. But anything that accepts H plus. So here we have this HC2H3O2 plus NH3. This HC2H3O2, this is acetic acid. It gives off an H plus. So if you go from this side to this side, you see it loses the H plus. Therefore, it's the acid. Okay. The NH3 goes from NH3 to NH4. Therefore, it accepts the H plus. Therefore, it is the base. Okay, so the acid and then the base. Now, we often have, in the Bronsted-Lowry definition, we have conjugate acid-base pairs. In the reactants, we always have an acid and base. Okay, and in the products, we have a conjugate acid and a conjugate base. So basically, we look at it backwards. What happens to it as it goes backwards? So this C2H3O2, this, as it goes backwards, accepts H+. So this to this is accepting H+. So therefore, it is the conjugate base, or CB. I just call it the CB. And then NH4 goes from NH4 to NH3. It gives off the H+. So therefore, it is the conjugate acid. And actually, I need to fix this because it should be. This should be positive. Okay, and then let me label these. So acid, base, conjugate base, conjugate acid. Again, the conjugates are always in the products, and the acids and bases are always in the reactants. Have we done practice on conjugate acid, conjugate bases? Do you guys remember from earlier in the year? Yes? No? You think so? Not sure? Is this familiar? I can't remember if we did it in Unit 1. I think we do it in Unit 1. We go over this and we practice it. James, stop shaking your head. I know you know it. Stop it. No, I'm just kidding. Yeah, so basically, acid and base, pretty simple. And then conjugate base, conjugate acid, you just look at it in the backwards direction. What's happening going backwards? Okay, it's always, and the one mistake I see most people make when talking about conjugate acid, conjugate bases, they put conjugate in the reactants. It's never in the reactants. It's always in the conjugate's always in the products, okay? So you have acid base and reactants, conjugate base, conjugate acid in the products. Okay, so first thing, before we talk about Ka and Kb, we have to understand this idea of this auto-ionization of water, because this is really where the pH scale comes from. This idea that water will auto-ionize, meaning that when we say we have water, and when we have water, just pure water, it's not all of the molecules are actually H2O. Some of them are actually H3O plus and OH minus. This is just because the water molecules are bouncing around, hitting each other, and sometimes basically the hydrogens rub off from one water molecule to the other. Okay, and we call that auto-ionization. And that's and then what happens is about 2 in every 1 billion water molecules. So it doesn't happen that much, but sometimes the water molecules transfer hydrogen to another water molecule. And we'll get H3O plus and OH minus. Okay, it's just because these bonds between the hydrogen and oxygen are pretty strong, but they're also strong between the other. We have the hydrogen bonds between this hydrogen and this oxygen, and sometimes those hydrogen bonds cause this one to actually break off. It just breaks off. It happens. I don't know. It just does. It is what it is. Okay. So in pure water, what we actually do is we have a hydronium ion concentration. That's what we call H3O plus, hydronium ion, this hydronium ion. We have a concentration of 1 times 10 to the negative 7. And OH minus concentration of 1 times 10 to the negative 7. That's in pure water. Pure water. Okay. And when we multiply those two things together, we get this constant we call Kw. This Kw is called the autoionization constant. And it is equal to 1 times 10 to the negative 14th, which is the H plus concentration times OH minus concentration. Now, one thing great for us is that this multiplication here, the H plus times OH minus, this is always constant. Doesn't matter if we have an acid where we have lots more H plus. Okay, this is always constant. These two are not always the same, but when we multiply them together, we should always get 1 times 10 to the negative 14th. It just so happens to be that way. It works out really nicely. Okay, we can do a lot of things with that. Okay. And no, I didn't really. No, I didn't do it on this one. My old one used to have the example of it, but I guess I never added that to this one. So basically, if H plus goes up, OH minus goes down. If OH minus goes up, H plus goes down. But this multiplication, these two multiplied together, will always give us 1 times 10 to the negative 14. Okay. So that's kind of where the pH scale comes from. Because 1 times 10 to the negative 14th, the negative log of that is 14. That's where the 0 to 14 comes from. But again, it can kind of lie outside that range. There are times where the pH is higher than 14 or lower than 0. It can happen, just not very often. If you know all of this stuff right here, we can do a lot of the calculations for just regular acids and bases. So if we're talking about strong acids, strong bases, this is pretty much all we need to know. This is really useful for weak acids and weak bases as well, but it doesn't tell us the whole story all the time. And again, we've kind of worked with this stuff previously, and there's some practice for you guys to do today. Okay, so again, strong acids totally dissociate in water. So if we have a one molar solution of HCl, then our concentration of H plus is 1 molar. NaOH is a strong base. If we have a 1 molar solution, then OH minus is 1 molar. And there's a little typo here, so I'm going to fix that. NaO. Okay, it's important that you do memorize these strong acids and strong bases, because everything else is a weak acid or weak base, right? So all these, are strong acids: HCl, HBr, HI, HNO3, H2SO4, HClO3, HClO4, and HiO4. Lots of typos in this thing. Okay, and then really quickly, we're going to talk about Kas and Kbs. So basically, weak acids and bases only dissociate partially in water. So if you look here, this is a strong acid. Strong acids totally break apart. So you can see here, all of them are broken apart into their ions. So there is no Ka or Kb value for strong acids and strong bases. Whereas weak acids, only very small amounts of it break apart. Okay, so it doesn't go all the way to completion. The reaction, or the solubility, the HA to HA plus to H plus and A minus, doesn't go all the way to completion. I really should have written it that way. What was I doing when I made this? So this is what I mean. So it would be like this. Strong HA goes completely to H plus plus A minus. Whereas weak is in equilibrium with H plus plus A minus. It looks like that. right? So here, like strong goes all the way to H plus and A minus, weak is in equilibrium. It goes back and forth. So we have an equilibrium that's being established. We have a ratio of products over reactants, okay? And that ratio is what we call the Ka statement. And that's what we're showing here, okay? So the Ka is products over reactants, okay? The larger the Ka, the stronger the acid, okay? The larger the Ka, that means that more of the acid dissociates into H plus and A minus. Okay, that means that we have a stronger acid. So the larger Ka, large Kas strong acids have larger Kas. And then the same thing goes for KBs. KBs will have the products over the reactants, and the larger the Ka, the larger the Kb, the stronger the base. And that is where we're going to stop today. So you look at these Kb and Ka values, you'll see that the values are usually 10 to the negative something. Oh, I don't know why they put the bases in opposite of the acids. It's weird, but whatever. So the strong acids are on top here, the stronger acids, and the stronger bases are on the bottom here. Okay, and that's it. Stop there. We will talk about strengths of acids and bases.